All right. In the previous videos, we introduced linear combination, right? But I would like to start with a very short recap of the 10 minutes ago by introducing like how we were deeming sometimes vectors as data points, right? And when we scalarly multiply a data point with varying scalars, I mean linearly combining this one vector with different scalars, we would see that all of these points would live on a surface that's on the same direction with this guy, right? And we also covered that linear combination of these two vectors, and if I have different a and b numbers, I will have, when I combine them, I will have different yellow vectors. So okay, so far so good. So it means that if I could I could actually get a vector using these two vectors. I can get a vector yellow from red and blue, and also approaching the same way, I can get a point on the yellow point by linearly combining these two vectors or points, right? So by linearly combining, I can get a new point. So I am going to, based on these two things, I'm going to introduce a geometric interpretation of linear combination and argue what linear independence imply in that interpretation. So if I were to think about, so in this three-dimensional space, and it is going to start rotating in a bit. So in this let me start this. So in this three-dimensional space, right? So X, Y, and Z, and you see on the left, let me stop this. On the left, I have just one vector in this three-dimensional space along the X dimension. So if we were to imagine all linear combinations for X is equal to a times 1, 0, 0. I would like you to I recommend you to stop here, not stop here. I'm gonna tell you to stop here. Let me give you a few more explanations. So I'm interested in finding the linear combinations of all points, data points, of a times 1, 0, 0. So note that 1, 0, 0 is a point. It's not necessarily a vector. It can be a point. And a times 1, 0, 0 is also a point. So if I had one red marker that if I were to go ahead and point, just paint on this three-dimensional space, the point that I get from a times 1, 0, 0 for some a, if I were to change the a from, let's say, 1 to 1.1, 1.2, 1.3, and if I were to keep, if I have the patience and the time of the universe, if I were to paint all the points that I could get from linearly combining this one vector, what would I get? What kind of shape I would get with this paint. Here I would like you to pause if you don't have an answer and think about it, because the answer is going to if you can get the answer from your own imagination, I think it is going to help you comprehend some of the more complex tasks, topics that are going to come up. But the answer is, if I were to go ahead and paint all the points, I would get a straight line. All the points are going to live on the direction that's depicted by 1, 0, 0, and I could have a point 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 3, 0, 0, 1.200, and all of these data points have no dimension but the direction that's demonstrated by the x-axis. All right, let's go ahead and make this a little bit fun. So let's say now I have two vectors I'm linearly combining, 1, 0, 0 and 0, 1, 0, right? And I'm living on this three-dimensional space, and I would like to find all the linear combinations of 1, 0, 0 and 0, 1, 0. What does all linear combinations mean? I'm going to keep changing A1 and A1 and A2, just like I did in the previous video when I was getting a yellow vector from red and blue vectors, and I would paint all the points that I get for any A1 and any A2. So pause and think what you think that would get. Otherwise, if I could paint everything, I would get the plane. So this I would get XY plane. So there won't be any dimension along the third dimension, and I would get 1, 2, 0, 5, 6, 0, all of these A, B, 0 points. And you see that this linear combination that I show here actually insinuates that I can the set of points that I can get from these two vectors. In the future, we will have names for these two vectors, and we will have names for the set of points that are highlighted, right? So I would like you to see here that although the set of points that live on this shadowy plane, this blue, baby blue plane, although the points of this plane look like they have 3 indices for their locations, you can clearly see that the third index is always 0. They live on a 2-dimensional space, right? And I will argue that even though one of the elements are not clearly 0, in a bit, I will argue in a bit that even though one of the elements might not be 0, you can still live on a 2-dimensional space, even if you have 3 different indices to describe where you are. So let's change the problem. Same problem, instead of I'm changing the vectors that I use to constitute the set of points. So instead of 1, 0, 0 and 0, 1, 0, I'm using, if I were to use 1, 0, 0, 0, 0, 1, then I will have no dimension along the second dimension, no point along the no variation along the second dimension. I will have again another plane composed by 2 vectors, created by 2 vectors. There will be a name for these 2 vectors in the future, and although there are 3 dimensions, there are actually not 3 dimensions. So if I were to have 3 distinct dimensions, if I could combine A times the first one, B times the second one, and C times the third one, you guessed it, I will cover the whole 3-dimensional space. So I can actually get any point in this 3-dimensional space. So far so good. Now I would like you to think about, if I were to linearly combine all of the points that I get by all of the points that I get from the linear combinations of this vector. Not that this is this vector, there's only one vector that's directing in one direction. If I'm taking my A and I'm changing the A, and with my red marker I'm pointing every A times this number 301, this vector 301. So A times 301 for A equals 1, A equals 1.1, A equals 1.11, A equals 1.2, A equals whatever, right? So if I were to paint all the numbers, I will get all the vectors. I will get a line that's on the same direction as 301. Now, if I were to make it a little bit more difficult, so if I have now 2 vectors, and they have their own directions. 301 has one direction in this 3-dimensional space. 121 has its own direction, and I'm getting the linear combinations of these 2 guys, right? So I'm gonna get my pen again. I'm gonna select one A and B. and combine them and then mark it. Change the A and B, mark it. Change the A and B, mark it. So if I were to paint all the points, I will again get some surface like this. Note that this surface is a plane. In a three-dimensional, it looks like it's a three-dimensional world, but note that I have no chance of leaving that plane. I'm actually living on a two-dimensional world. I might as well describe where I am in two-dimensional, two numbers, even though I am living on a three-dimensional world. Please note like what I'm very vaguely and implicitly trying to describe here. Like all of these things, they are going to come up. For those of you who have already taken advanced linear algebra, they might be understanding or getting what I'm trying to establish here. There are names for these vectors, and there are names for describing where you are on this plane, even if your these vectors are three-dimensional, even if you're climbing a hill, like you're going this way, you're still on a two-dimensional world. But the more important, interesting thing is if I were to add a third vector, just like we did naively in the first one. So I had 1, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And if I were to combine linearly ax plus by plus cz for all a, b, c numbers, we have discussed that we could get a three-dimensional space, the whole space. Now, with that hope, I am introducing the third vector to constitute my third dimension, hoping that I could get the whole space. But there's one thing I realize: they are not linearly independent, meaning I can get. Remember, I said like x1 minus 2x2 plus x3 is equal to 0, meaning I can get x3 from linearly combining x1 and x2. So if I were to linearly combine these three vectors, I will still get a plane. So that's the value, that's the importance of linear independence. So if I cannot move, I think that I could move by introducing another CZ, move from this plane, and I can have a new life for myself. I'm just going to leave this planet, but the linear combination rules say no. Like the thing that you think that it is going to help you fly from this plane is already created from elements of this plane. So there's nothing new. There's nothing new. No new dimension for you to start flying, right? Or leaving this plane. So you're still on this plane, even if you keep adding new vectors that you create that you get from this plane. It's not going to help you get a new data point that's not on this plane. So I hope this geometric interpretation, like by introducing this geometric interpretation, I aimed to provide one importance of linear independence and how it's going to relate to machine learning. And I hope that I like activated some of the neural brain cells that are going to be useful understanding some of the more advanced complex topics in linear algebra in a few days.